So thank you everybody for staying on. So I'm going to be doing a slightly different talk now in the fact that it's not active research, it's actually a summary of sort of the last decade or so of carbonatite related research from some fairly large projects such as SOS Rare and High Tech Outcarb. So I'm going to be talking about the Goldilocks effect of getting rare earth deposits to actually form within carbonatites related to rift zones. So how we need the processes just right to line up to actually form a rare earth deposit in a carbonatite. So for those of you who aren't familiar with carbonatites, I'm going to very briefly introduce them. For those of you who are, please bear with me. So carbonatites are essentially igneous rocks that are composed of over 50% carbonate minerals. So not the normal silicate minerals that we would expect to find in igneous rocks. It's much more carbonate based. So their appearance can vary quite considerably. Here's just some examples from the larvae on the screen. You can get some quite clear calcite crystals forming like these, or they can form these sort of dirty orange brown carbonatites as well, which tend to be much more manganese and iron rich. But we actually find carbonatites all over the world. They're not actually as rare as people think. This is a map that was all the known carbonatites back in 2008, and that was 527 known occurrences back in 2008. And we've even got one here in the UK where I am at the moment, right up there in Scotland. But there's only one that is still active in the world today, and that is obviously Aldenyai Lengai over in Tanzania. And for those of you who have not been onto YouTube and spent quite a few hours looking at videos like I have, I strongly suggest you do. They form, I'm very briefly going to just show you a video of them. They form these really sort of low viscosity, really running, beautiful lava flows. And they're actually a lot colder than normal magmas. So a normal magma is around about 1200 degrees, whereas a carbonatite before it erupts is sort of 800 to 900 degrees. So if you haven't done it, I have put the YouTube link on there. Go have a look. They are absolutely beautiful. Hopefully you could hear me over all of that. But they are great if you do want to spend some time on YouTube. But how do these magmas actually form? They are weird, they're peculiar, they're carbonate based rather than silicate based. Well, there are three commonly accepted theories, and that doesn't mean that one theory is right and the two others are wrong. It is much more likely that carbonatites in different locations and different tectonic settings actually form in quite different ways. And that's really evidenced by the wide variety of chemistry that we see within these types of deposits. Now, the first theory that we have is that carbonatites are actually primary magmas that are formed from mantle melting. And we need actually very small partial melting of the mantle to form these. I'm talking less than 1% partial melting. But it tends to be of a carbonate rich and a metasomatized mantle. So it's already a little bit of carbonate in the mix as well. Now, this is usually from something like decompression melting, so where we've got a natural geotherm underneath that is then slightly decompressed, and the mantle goes over the solidus just a small part, and that allows a little bit of mantle melting. It can happen from the addition of volatiles as well, but that does tend to form a bit more wider scale melting in that regard. Now, if we do get slightly larger degrees of mantle melting, we can form carbonatites in two other ways. So if we've got an alkaline silicate melt that forms due to slightly more mantle melting, we can actually still get a carbonatite forming as a result of fractional crystallization and magma differentiation. And we get the carbonatite as sort of a residual liquid after that happens. Or from, again, the same parental mantle melts, we can then get liquid immiscibility. So as an alkaline silicate melt cools and is depressurized, the carbonate liquid can no longer mix with the silicate liquid and they actually unmix. So two immiscible melts there. So there's three different methods of forming them. Now, these processes can happen in a variety of different settings. We can find them in post-orogenic settings, so where we've got collapse of an orogeny and slight decompression melting of the mantle. We can get them in subduction zones, where we get addition of volatiles, or we can have them in continental rifting, where we get decompression of that underlying mantle there. Now, Continental rifting is actually one of the earliest recognized tectonic settings for carbonatites. So it's actually one of the best well-known, the best researched. And they tend to form quite long linear trends of both carbonatites and also alkaline rocks. Tends to be a lots of rare earth deposits within these systems that are associated with iron-rich carbonatites. So where we've got a lot of magma fractionation to form something more iron-rich, that's where we typically get the rare earths in these systems as well. And we also often get niobium enriched in these systems. Now, possibly the most famous rift associated with carbonatites is obviously that of the East African rift zone. We've obviously got the rift that is wrapping round the Tanzanian craton just here, because it's easier to rift that warmer, thinner, younger lithosphere rather than the older, thicker lithosphere in the middle. And then we've also got volcanic activity occurring on all of the limbs of that East African rift zone there, where we've got the stretching, the thinning of the lithosphere, and decompression of the underlying mantle. Now, the rifting is most advanced and mature in the northern section, as we all know, and the southern section is much younger and less advanced rifting. And this different state of rifting really affects the nature and the chemistry of the magma that's formed as a result of that mantle melting. So in the younger sections down here in the south, we've got much more minor stretching and rifting, and that means we've got only slight decompression of the mantle, and that's where we're able to form our carbonatites. Whereas up in the north, we have much greater stretching that continues, rifting is much more advanced, and we get much more mantle melting there. So if we actually look at the chemistry of the volcanism that we see and the different igneous deposits that we see along the length of the rift here, green is alkaline. So this is where we've got mantle melting around about 1 to 5% partial mantle melts. As we go further down, we have got carbonatite shown in dark blue. And then where we've got both within a deposit, it's shown as a light blue. So we can really see that difference with the carbonatites starting to come in around about here, where the rifting is much younger, whereas the much older, more advanced rifts, we tend to get that more alkaline system forming. Now, although carbonatites are carbonate based, their mineralogy is fairly complicated. There's a massive variety of other minerals in there as well. So 280 minerals recorded in carbonatites to date. Got silicates, sulfides, oxides, halides, phosphate, all in there. And the ones that are bold on the screen, those are the ones which are associated with rare earths or contain rare earths. But how do the rare earths actually get in there? Why are they so important within these sorts of carbonatites and alkaline settings? Well, it's really as a result of the different types of processes that all add up to form these deposits. And they're always based on really the sort of the behavior of the rare earths that we are actually looking at. Now, rare earths are highly incompatible. So that means they prefer to be dissolved ionically in a magma or a fluid rather than in a solid crystalline form. And that means that they tend to be much more enriched in the residual liquids. Now, bearing in mind, we are looking at sort of very low concentrations of rare earths in the mantle. Even if it's an enriched mantle, we're still talking, very low concentrations. And we need to get it up to economic levels of like 1% minimum. Bonobo, which is a world-class deposit, is 8 to 12% rare earths. So we really need to do sort of thousands to tens of thousands times enrichment to get it from mantle levels all the way up to sort of the rare earth enrichment we need to form our deposits. And that's mostly done using 5 different processes that are listed there on the screen: partial mantle melting, magma immiscibility, crystallization of the magma, hydrothermal remobilization, and also lateritic weathering. Now, that first enrichment process that we need is actually the formation of the magma itself. And it tends to be melting of areas of mantle that are enriched in incompatible elements already, either due to something like fluid metasomatism, addition of carbonate minerals. So we're talking somewhere near a subduction zone or getting some volatiles from a plume, for example. But as I said, it's very low partial melts of the mantle. We're talking anywhere up to about 1% partial melts. Now that means that all of the incompatible elements are going to rush into the very first mantle melts that are formed. This line here shows a 5% mantle melt, and it's a concentration of the sample in the mantle divided by chondrite, so it's normalized. And we can see a really high enrichment in the more incompatible light rare earths as opposed to the heavier rare earths. And that's a 5% mantle melt, so you can sort of see what a 1% mantle melt would be, much more enriched. Whereas if we continue to increase our mantle melting, can see that actually it's a 10%, 20%, 40%, those rare earths actually start to become diluted. So we need very small degrees of partial mantle melting. Anything more than that, it's actually going to be diluting our rare earths. But if we do form something slightly above a carbonatite, so if we do have more partial mantle melting and we form an alkaline silicate melt instead, then we can still get enrichment of our rare earth elements through different processes. Now, as our alkaline melt continues to cool, as I said before, the carbonatite cannot remain mixed. It starts to unmix, it's immiscible and it separates. And rare earth elements have what we call a high distribution coefficient in carbonate-rich melts, which means that essentially they rush into the carbonate melt away from the silicate melt. Now, this graph shows the distribution coefficient of sort of our rare earths, our lanthanum and our lutetium, in a carbonatite divided by a silicate melt. So essentially, anything above 1, our rare earths are going to be heading into our carbonatite rather than staying in our silicate melt. And if we look at what these symbols are, if we add water into the mix, then actually we get really high distribution coefficients, which means that the rare earths really strongly not only partition into the carbonatite, but also really are increasing the transition from the silicate melt into the carbonatite with the presence of water. And in rift-related zones and also in subduction-related zones where we have carbonatites and silicate melts, these tend to be very water-rich and tend to be quite volatile-rich. But magma crystallization itself does actually increase our rare earth enrichment as well. If we do actually manage to trap our magma at depth in some form of magma chamber rather than actually erupting it straight up to the surface, then it gives it time to sit there crystallizing, differentiating. So initially what we have is we get calcite crystallizing out of our carbonatite, and these tend to be rare earth poor, and that's because our rare earths are incompatible, and that means that they want to stay in that residual melt. And that means that as we continue to fractionate and we continue to actually crystallize our magma, that residual melt gets much more rare earth rich and much more iron rich. Now, if that residual melt stays down there and is trapped in the crystal chamber, actually, yes, it's sat there stewing in its own juices. The rare earths are more concentrated, but still they are diluted by whatever is surrounding it in the magma chamber. However, if we manage to siphon off those late stage melts, those really iron and rare earth rich melts, we then get sort of late stage intrusions, late stage veins that are much more concentrated in our rare earth elements. Now, as our carbonatite cools and crystallizes, it also starts to exhaust fluids, and these tend to be a mix of water, carbon dioxide, and also ligands. So things like fluorides, chlorides, carbonates, phosphates, for example. And these complex with the rare earths, and they can actually preferentially remobilize them from a deposit that's already formed. And that means that they can strip away some of our rare earths. It tends to be preferentially either light rare earths or heavy rare earths, depends on the ligands that you've got. And these apatites that you can see here, these are CL images. You can see the porous nature, you can see the fragmentations of the apatite. That's actually recording evidence of that remobilization process. Now, this process can be a blessing or it can be a curse. It can help concentrate your rare earth elements, so actually leave behind your heavies, which are the more valuable ones, and take your light rare earth somewhere else, or it can strip everything out. So it's really, it can be a blessing or a curse in this regard. And the last process that we've got for rare earth enrichments is our lateritic weathering. So this is where we've had a rock that has become enriched by all these processes. We've formed our rare earth deposit. It's got lots of rare earths in it, but maybe not quite economic levels. And this then gets pushed up to the surface, it gets uplifted, it gets exhumed until it is at the surface through erosion processes. Now that carbonate rock exposed in a hot, wet environment, like tropical environment, for example, will very quickly become altered and weathered, get percolation of the meteoric water through the deposit, and that will actually leach out the rare earth and then precipitate them in much more concentrated lenses at a redox boundary lower down. So this is forming high-grade mineralization. But again, this process can be a mixed blessing. Yes, it is advantageous because it forms a deposit that is more concentrated. The carbonatite itself is softer because it's weathered and altered, but actually it forms a range of secondary minerals that can sometimes be harder to process and actually recover the rare earth elements within them. So I'm aware that I'm running out of time, so I'm just going to very quickly summarize that. So all of these processes, it's really a case of everything needs to be just right. It needs to form a rare earth deposit from which we can actually recover the rare earths in a carbonatite at a rift zone. It needs all of these processes to be just right. Too much of something can destroy it, or too little of something, it might never actually form. So what we need is a young, immature rift that allows low degree partial melts. If we do get into our alkaline silicate range, we can still form our carbonatites from magma differentiation and a miscible separation of the carbonate liquid. And that's all enriching our rare earths. But we need that late stage separation of our iron rich and our rare earth rich systems. And that allows us to form these very higher grade deposits. Late stage processes like hydrothermal remobilization and lateritic weathering can enhance a deposit, but it can also cause complications as well. So thank you very much for listening.
Okay, thank you very much, Holly, for the nice discussion on the carbonatites and their enrichment. I think I'll take only one question, and then the rest we can have them on the chat, and you can address them later. Yes, Rune Larsen?
Yeah, thanks. Thanks a lot, Holly. That was an excellent summary of the carbonatite conundrum. So since we have little time, I will go straight into it. You seems to favor very low degrees of partial melting, although you do mention liquid immiscibility. I have worked quite a lot with the silent igneous province, not so much with the carbonatites, but I mean still, when we're looking at the ultramafic volcanic conduits, we actually do see very complex alkaline clots. I mean, we are at 1 gigapascal, so when the pressure is really high. And you know, I would find it really difficult to imagine very low degrees of partial melting making it all the way to the surface without some havoc on the way. What do you think?
Yeah, I mean, obviously I haven't worked on the deposits that you are looking at, but we do find elements of alkaline or alkalinity in other types of systems. It might be that you've got some form of earlier, very low degree partial melting that is then being brought up by something that is sort of grabbing things and bringing them up to the surface, or it could be that you've actually got some form of differentiation and segregation, sort of an immiscible system that's forming these sort of enclaves and clods that you're talking about. So we do see sort of alkaline related things in more advanced systems. But if you think about a rifting environment, it's got to go through lots of different stretching and stages before it gets to a full rift. So actually, although we see some of these alkaline systems in the north that are sort of more alkaline now, it could have been that there were carbonatites there and they were forming a carbonatitic melt in their early stages, and then actually the alkaline system took over. If you then advance that and continued advancing that, you would get to something that is heading towards a much more mafic area. So what happens to your early phases? Do they get digested? Do they get sort of reworked? And it could be that something like that is happening in those sorts of systems where it is much more mafic, much more evolved now, but what was it before?
Okay, very short. Could it simply be that the northern part is more deeply eroded? Do you have higher pressures up there?
Sorry, I didn't catch that.
Oh, the northern part where you have mostly alkaline magmatism, is it simply just because it is more deeply eroded? Higher pressures, like, yeah.
So in terms of the different levels that we can get, obviously our alkaline systems can stall at depth, but you can get carbonatites forming at any level. Essentially they can form, we're talking from kilometers deep all the way up to the surface, so it could be a preservation potential, but there is sort of this overriding thing that actually the rift is much more advanced to the north, and the fact that you're forming those alkaline systems in sort of huge numbers suggests that actually it's progressed past the point where it can form carbonatites.
It's a good point. Thanks.